If you are looking for the absolute most urgent flashpoint in global climate change, you really have to look north.
Hmm.
The Arctic is in crisis, and speed of that crisis is, well, it's genuinely alarming.
It is.
Since 1979, the Arctic region has warmed nearly 4 times faster than the global average. We're talking about runaway acceleration, not just, gradual warming.
And that speed differential is exactly why researchers are looking everywhere for solutions,
Hmm.
urgently.
Right.
When the pace of reducing greenhouse gas concentrations hasn't kept up with this rapidly accelerating regional warming, scientists have to look at complementary approaches.
Things like geoengineering.
Right, often grouped under solar radiation management or SRM. The
Yeah.
fundamental idea is to, well, temporarily reflect sunlight back into space to buy time.
To reduce temperatures while the world transitions to zero carbon.
Exactly. And because the feedback loops in the Arctic, like the ice albedo effect, are so powerful, it's an obvious target for a regional intervention.
And the specific technology we're diving into today, the one that really does sound like something out of a sci-fi movie, is Marine Cloud Brightening, MCB.
Hmm.
For you, we've taken a deep dive into a powerful new multi-model comparison. This research simulated injecting tiny particles of sea salt aerosol, or SSA.
Into the atmosphere over the open ocean in the high north, specifically between 60 and 80 degrees north latitude.
So our mission today is to get to the bottom of the trade-offs.
Right. If we scale up this sea salt injection over time with the explicit goal of maintaining the Arctic surface temperature near its current value.
Even under a moderate warming scenario.
What happened?
And just to give you that context, when we say moderate warming scenario, we're talking about SSP2 4.5.
Which is a middle-of-the-road scenario. It assumes some climate policy, but still leads to roughly 3 degrees Celsius of global warming by 2100.
So a huge challenge. Does MCB actually work locally? And maybe more importantly, does it cause catastrophic unintended side effects across the globe?
Okay, let's unpack the core physics first, because I think understanding the mechanism is really key to understanding the uncertainty later on.
Let's do it.
So the mechanism hinges on something called the Toomey effect, which scientists identified way back in 1974.
Okay.
Essentially, clouds are made of tiny water droplets. For those droplets to form, you need microscopic particles for the water vapor to condense onto.
These are called cloud condensation nuclei,
Yeah.
CCN.
Exactly. And over the ocean, those are naturally just sea salt particles.
Right. So the air is already full of these invisible anchor points for moisture.
It is. The MCB strategy is simple in theory. You inject massive but controlled amounts of these tiny man-made sea salt particles into the atmosphere just below the marine clouds.
And by doing that, you're just dramatically increasing the number of CCNs available.
You are. And when you have more CCN, the available water vapor gets distributed among a far greater number of droplets.
Which means
It means you increase the droplet number concentration, but you simultaneously decrease the average size of each individual droplet.
I like the analogy of a fixed amount of dough. You can make a few big cookies or dozens of small ones.
That's a perfect way to think about it. And a cloud made of many, many smaller droplets is optically thicker.
It looks brighter.
Precisely. It reflects more incoming solar radiation back to space. This process brightens the cloud, which reduces the energy hitting the surface below, and that's your cooling effect.
Okay, but anyone who's ever looked at the sky knows clouds are incredibly complex, they're messy. This sounds elegant, but where do the real-world complications creep in?
Oh, they creep in immediately. And this is where the modeling becomes so critical.
Okay.
We have to consider what these smaller droplets do to the life of the cloud itself. So while smaller droplets increase reflection, they can also potentially suppress precipitation,
If it's not raining, the cloud lives longer.
which increases the cooling effect. That's a positive feedback.
But there's a counter effect, isn't there?
Yes, there is. Conversely, a cloud of smaller, brighter droplets can also increase cooling at the cloud top, which can destabilize the cloud, cause more evaporation.
And a shorter cloud lifetime.
Exactly. So if the cloud evaporates faster, the total cooling decreases. Whether the intervention ultimately makes the cloud live longer or shorter is a huge uncertainty.
So scientists are running a global experiment on a virtual system where the variables for how long a cloud lasts are still, major sources of debate.
That's a good way to put it.
Yeah.
That said, we do know the underlying physics works. We see it in nature.
Right, these natural analogs.
We have powerful ones.
Mhm.
For decades, we've seen high-latitude volcanoes release massive amounts of sulfur dioxide, which acts as CCN and brightens clouds.
And the most famous example is probably ship tracks.
Absolutely. The lines of condensed water left by shipping exhaust, they clearly show that putting aerosols into the marine atmosphere directly brightens the clouds.
So if the physics works, the next critical question, especially for you listening, is the sheer scale. How much of the stuff do we actually need to pump into the air?
And this is where this multi-model study, the very first one for Arctic MCB, provides a crucial but pretty worrying answer.
They used three big Earth system models, UKSM-1, CESM-2, and E3SM-V2.
And right away, the models revealed the biggest weakness in our current understanding.
Which wasn't if it works.
No, not at all. All three models agreed it successfully cools the Arctic. The uncertainty was the radical difference in the required scale of the sea salt injection.
And let's be clear about the range here. This isn't a small difference, like 10 or 20%. It's vast.
It is staggering. The Community Earth System model, CESM-2, was highly sensitive. It required the least amount of sea salt to get the job done.
Okay, so that's our baseline.
Then you have E3SM-V2. It required about twice the mass of CESM-2.
Twice. Already big jump.
And then there's the outlier, UKSM-1. It required approximately 10 times the mass that CESM-2 needed.
10 times. That's the difference between planning for, say, a manageable fleet of ships and planning for a massive, globally resource-draining industrial operation.
Exactly. This 10x uncertainty is really the central takeaway on feasibility. It all stems from what are called microphysical parameter differences.
Which is basically how each model handles those complex cloud interactions we just talked about.
Right. Tiny, uncertain parameters that scientists have to tune in the code. For example, how quickly small droplets turn into rain. That's called droplet autoconversion.
And these small variables are tuned differently across the models.
And the result is that one model needs a spoonful of sea salt, while another needs 10 spoonfuls to get the same cooling. We just don't have the real-world data to know which one is right.
It makes any kind of policy or investment planning almost impossible. But, okay, let's assume we figure out the scaling. Did the intervention actually work in the Arctic?
Locally, yes. It was a success across the board. All the models showed substantial regional cooling.
And the main goal, the sea ice.
They achieved it. They maintained the Arctic sea ice extent, kept it near the target values, and prevented those devastating summertime ice-free conditions.
Okay, this brings us to what I think is the most counterintuitive part of the findings, the seasonality paradox. You're reflecting sunlight, so you'd think the cooling happens in the summer, when the sun is out. But the sources say the maximum cooling happens in the dead of winter.
This is where it gets really interesting, and it reveals a critical climate dynamic. The radiative forcing, the actual reflection, does peak in the summer.
As you'd expect.
But the effect is delayed and amplified. By reflecting so much energy in the summer, you're preventing the ocean from absorbing all that heat.
So the ocean is storing less heat energy to begin with.
Precisely. Then, during the long, dark winter, when the ocean usually releases all that stored heat back into the atmosphere.
It's just less heat to release.
Exactly. That reduced ocean-to-air heat flux, combined with the stable winter atmosphere, means the biggest temperature drop happens when it's darkest. There's a powerful delayed feedback.
Which also has practical implications. The study emitted the salt year-round for the simulation, but in the real world, you'd likely just do it in the summer.
That's right. But we also have to be clear about the limits here. Two of the models ran into an intrinsic ceiling. Specifically, in UKSM-1, the radiative forcing just saturated. It hit a hard upper limit.
Meaning you could pump in more and more sea salt, but the clouds literally couldn't get any brighter.
That's it. The cooling effect flatlined. And this saturation is why both UKSM-1 and E3SM-V2 ultimately failed the long-term test. They overshot their target temperature by the end of the century.
So there might be an upper limit to how much warming this can actually offset.
It suggests MCB may only delay, not permanently solve, ice loss under very high warming scenarios. Only CESM-2, the most sensitive model, kept the temperature on target.
Okay, so we've proven it works, with some major caveats on scale and limits. Now, let's pivot to the really crucial part. The side effects.
The unintended consequences.
With other proposals, like stratospheric aerosol injection, there were huge concerns about shifting tropical rainfall. What happened here?
And this is probably the most encouraging finding of the whole study. Arctic MCB appears to cause significantly fewer extrapolar climate impacts.
So the cooling stays local.
For the most part, yes. It's highly confined to the high northern latitudes.
What about global rainfall? Disrupting agriculture in the tropics is always the big fear.
The models showed no robust or statistically significant precipitation changes in regions remote from the Arctic.
That's a huge deal.
It is. Take the Sahel region in Africa. It's highly vulnerable, and it saw some worrying changes in those earlier SAI simulations. With MCB, there was very little consistent change across the models.
So why? Why is this so much more localized?
Well, the sources suggest the forcing is just fundamentally different. Stratospheric injection puts aerosols high in the atmosphere where they spread globally. That creates a broad change in the energy balance.
Which can mess with tropical weather
Right.
systems.
MCB is a low-altitude, cloud-level intervention. The forcing is so localized near the surface at the pole that the tropics are just far less sensitive to it.
Localization seems to be a major advantage then. Okay, what about the Atlantic Meridional Overturning Circulation, the AMOC, the Atlantic Conveyor Belt?
So under the baseline warming scenario, the models projected a typical slowdown of the AMOC. That's what we expect.
And with MCB?
In two of the models, UKSM-1 and CESM-2, the intervention led to a substantial, though incomplete, recovery of the AMOC.
Wait, a recovery? So it actually helped push the system back towards its present-day state? That sounds like a massive co-benefit.
It absolutely sounds that way, and this partial recovery did explain some of the regional cooling they saw in the North Atlantic.
Here comes the necessary nuance.
Here it is. This is the most critical caveat in the entire study, which the researchers stressed heavily.
Tell us.
The model versions they used do not have a coupled Greenland ice sheet melting component.
No.
And in the real world, the massive input of cold, fresh water from a melting Greenland is a primary driver of the AMOC's decline.
So the models were able to recover the AMOC because they were ignoring the single biggest factor causing its slowdown in the first place.
Exactly. They were only seeing the effect of the surface cooling, not the massive freshwater input. So while the recovery they saw is a great sign, the real-world response is still highly, highly uncertain.
That is the perfect encapsulation of this kind of research. Immense potential paired with just profound uncertainty. So wrapping this deep dive up, what are the two core takeaways for you, the listener, trying to grasp the state of Arctic MCB research right now?
The first is high efficacy and low impact. Marine cloud brightening is physically capable of achieving substantial regional cooling and maintaining sea ice.
It works.
It works. And crucially, it seems to avoid those large-scale detrimental tropical side effects, like massive rainfall shifts, that we worry about with other methods.
But the second takeaway has to be that profound real-world uncertainty.
Absolutely. We saw a tenfold difference in the amount of aerosol required.
Yeah.
That's an insurmountable hurdle for any kind of current policy planning.
And we saw that saturation risk, suggesting there's an upper limit to how much good it can do.
And we have to remember what this study wasn't. It was an idealized climate study. It didn't address the practical questions: governance, technical feasibility.
Or the non-climatic impacts. What does dumping all that salt do to atmospheric chemistry or to the marine ecosystems right there in the deployment zone?
Exactly. Those questions are still completely unanswered.
Which leaves us with a final provocative thought for you to explore. The sources suggest a practical application would only happen during the short, sunlit summer months. Given that success is defined by maintaining that sea ice, how would a hyper-localized seasonal deployment strategy minimize the inevitable ecological impact on marine life while still maximizing the climate benefits necessary to stabilize the region for the whole planet?